Hey everyone, and welcome. Today, we're going to dive under the hood of database performance and talk about a super important but kind of overlooked tool in our toolbox, data compression. It's really the unsung hero of efficiency, and we're about to see exactly why it matters so much when you're managing data at scale. So, here's what we're going to do. We'll start with the big why. Why even bother with compression in the first place? Then, we'll uncover the secret sauce, the magic behind it all, which is finding redundancy. After that, we'll look at a classic algorithm to see how these patterns get turned into real savings. And finally, we'll get practical and talk about the real-world cost of using it. Okay, let's kick things off with our first section, why compress data? This really gets to the heart of a problem we're all dealing with, those hidden costs of digital bloat. But you might be thinking, hold on a minute. Storage is cheap, right? And our networks are faster than ever. So why on earth should a database admin spend precious processing power on compression? And that is the core question, isn't it? The answer really comes down to scale. First, you've got the physical disk space, what we call our data footprint. And sure, storage might be cheap per gigabyte, but it adds up fast when you're dealing with terabytes or even petabytes. But honestly, the real killer is often transmission. Think about it. Backups, replication, or even just pulling data from disk into memory for a query. Moving smaller, compressed data is just plain faster. So at the end of the day, we compress to save on two of our most critical resources, storage space and time. So we've nailed down the why. Now let's get into the how. How do you actually make data smaller without, losing it? Well, we're about to uncover the fundamental principle behind all of it, finding and getting rid of wasted space. So how in the world does that work? Is it some kind of magic? Because when you look at a simple string of text, like this one, just a bunch of A's, B's, and C's, it seems like the information is what it is. How can you possibly shrink that? Well, it's actually a lot simpler than you'd think. Instead of writing out every single character, what if you could just describe the pattern? Like 5 A's, then 3 B's, then 6 C's. That's way shorter, right? That is the magic of compression, identifying and exploiting what we call redundancy. And this gets to the core of what's known as lossless compression. It means we represent the information more compactly without losing a single bit of the original data. And for databases, this is absolutely non-negotiable. You can't just sort of have a customer's address. It has to be perfect every single time. All right, so now we get the concept. It's all about finding those repetitive patterns. So let's see how an actual algorithm puts that brilliant idea into practice. We're going to pull back the curtain on a classic method called Huffman coding to see how a computer can be taught to spot these patterns all on its own. So, how does something like Huffman coding actually pull this off? Well, the idea is pretty brilliant in its simplicity. Instead of giving every character a code of the same length, like in standard ASCII, it assigns variable length codes. The characters that show up all the time, they get really short codes, and the ones that barely appear get much longer ones. The really clever part, though, is how it guarantees you can get your original data back perfectly. The codes are what we call prefix-free, which just means no code starts with another code's complete sequence. This little design trick removes all the guesswork when you're reading the data back. It's foolproof. The process itself is, really methodical. First, the algorithm scans all the data and just counts up how many times each character appears. Then it starts building a tree from the bottom up. It finds the two least common characters, combines them into a parent node, and then just treats that new node as a single thing. And it just keeps doing that over and over, always combining the two lowest frequency items until everything is connected in one big tree. The most frequent characters just naturally end up closer to the top, which gives them the shortest codes. It's a simple, greedy algorithm that just plain works. Okay, so this all sounds amazing, right? We save storage, we make data transfers faster. It seems like a total win-win. But as anyone who's ever managed a production system knows, there is no such thing as a free lunch. So let's get into our final section and talk about the real-world cost. Exactly. So putting my DBA hat back on for a second, this all sounds great in theory, but what's the actual catch? What's the trade-off I really need to worry about when I'm thinking about flipping that compression switch on a production database? And this table right here, it lays out the fundamental trade-off perfectly. You gain a ton of efficiency in storage and in I/O, that's input-output, but you pay for it with CPU cycles. Every time you write data, the system has to spend cycles compressing it. And every time you read it, it has to spend cycles decompressing it. You're basically trading CPU power for savings on your disk and your network. Now, for a super write-heavy system, The cost of constantly compressing might actually slow things down, but for a read-heavy system that's always waiting on the disk, the faster data transfers you get from smaller data blocks could make things way faster. And that right there is the core trade-off every database admin needs to think about. If this quick explainer helped clear things up for you, please do us a favor and take a moment to like, share, and subscribe for more deep dives into the tech that powers everything we do.
Which leaves us with one final question to think about. Is compression a free lunch, or is it just a different item on the menu with a different price tag? The right answer, of course, really depends on whether your particular system is starving for more CPU or for faster I/O. Thanks for joining us.